Hi, I'm Ala Rustarola. Today I'm going to be presenting my solution to the problem of missing values in the MovieLens dataset. I'm going to be using the collaborative filtering algorithm with centered cosine similarity ratings. So my first step was to take copies of the data frame, separate copies for the users and separate copies for the items. I then had to normalize the data by subtracting the mean from each value. Now, since I was doing this separately for users and items, what I've done here is I've calculated a binary data frame by applying a lambda function to every value. And what the lambda function does is divide the value by itself if it's above zero, which leads to it being one. And if it's zero, it just times it by itself, so it stays zero. Then to calculate the mean, I've taken the sum along each axis. So for the user, it's axis 1, which means the rows. For the items, axis 0, which is the columns. And I've divided the sum I took from the original data frame with the sum from the binary data frame. And so what this leads to is a one-dimensional array with all the users' average rating and a one-dimensional array for the items' average rating. Following that, there's two for loops, one for the users, and so pretty much it just applies normalization, but only if the value is above zero. If it's zero, it just does nothing, and it does the same for the items. And so this normalization is required to calculate the centered cosine similarity. So as you can see in this equation here, up the top right, we have the value minus the average rating for that user or item if using the item calculation. So to apply the centered cosine similarity calculation to every value in each of my data frames, I've defined two nested functions. The first is the similarity rating function. So it takes the x data, the y data, the constant, which is either gamma or delta, which is required in the weighting, and n, the number of data points. And to store the information for the equation, I've defined three lists, one for the top, one for the bottom left square root, and one for the bottom right square root. And then so inside the similarity rating function is a recursive shared rating function. So first up, I've got the base case. If the count equals the number of data points returned from the function. Else, if two users have rated the same item, or two items have been rated by the same user, what it'll do is take the product of the two ratings and append it to the top sum list. And so for the bottom sum list, it'll append the I rating, and the bottom sum j list, it'll append the j rating. And then it'll recursively call the function and increment the count by 1. Else, if the two users don't have a shared rating or the two items don't have shared ratings, it'll just call the function again with the count incremented by 1. And so after all this, after I've defined that function, I apply that function to the two user or item vectors that were input to the main function. And then I take the sum of all the values that have been appended to the top sum, the square root of the sum of all the values in bottom sum I squared, and the same for bottom j, and then calculate the Pearson, which is in this equation just here, and I've added the epsilon to ensure that there's no division by 0. And for the weighting, the function returns the minimum of the length of the bottom sum I list and the constant, which is gamma or delta, and then it divides by gamma or delta depending on whether it's items or users, and then it gets times by the Pearson, and you can see it in this equation down here. Next, I have made my NumPy arrays for the similarity matrices and put two nested for loops. So for I in range 500, this is for the items. So for every item, it'll get every other item in range 500. If it's the same item, it'll pass, so it won't calculate it for itself. If they're different items or different users, it'll do the similarity rating calculation I just described in the previous slide and apply it to the numpy array. And I've done the same thing for the users. Now, step 3 is to store similar users and items. I've chosen nested dictionaries to do this. So I've got my similar users function. It's got the list of similar users and the indices below it as a separate list. The mask is the loc for the user. And so pretty much what this does is go through the whole numpy array, and if any of the similarity ratings are above eta or theta, if we're calculating it for items, it'll append the value, and it'll append the index, and it'll return a dictionary with the index and value. And so that function only returns a single dictionary with the user as the index, and its value is another dictionary of all similar users. And over here I've got the for loop, which pretty much creates a meta dictionary with all users and their value being a dictionary with all similar users to them. So for the main objective, step 4 is predicting the missing values, and I've done another nested function. The first one is missing values prediction. It takes in a data frame and an output, I think it was a numpy array, and inside I've defined functions for each different equation. So in the report, there's one for if there's similar users but no similar items. So that's equation 9, as we can see just here. Equation 10 is if there's similar items but no similar users. And I'll just explain one of them because they pretty much do the same thing, just with different data inputs. So for if there's only users, for the equation, we get the user average rating, which we calculated before. Now I've defined 2 lists to carry the top and bottom of the division in the equation. So when this function is given a user index and an item index, I first have a for loop to append all that user's similar users to the sum similar users list, which represents the bottom part of the equation. And for the top part of the equation, I need to factor in both the similarity and the rating given. So I've got another for loop, and that goes into the nested dictionary. It gets the similarity for each similar user and the rating. And so for the top of the equation, the similarity times the rating, and then it appends this to the sum sim with ratings, which represents the top of the equation. So then I take the sum of all these calculations, and the prediction equals the user's average rating plus the top list divided by the bottom list, and it just returns this prediction. And so for the only items, it's very similar. Equations 8 and 11 were pretty easy. 11 is just if there's no similar users and no similar items, return 0. Equation 8 is pretty much the other 2 equations, equation 9 and 10 combined together with the lambda value, which determines how much weight either the similar users or similar items give. And to apply these functions, I've got another nested for loop. And so for each user and each item, it'll go through a bunch of if statements to determine which equation should be applied. And it'll apply this to a temporary copy of the original imputed trained DS, and then predict all the missing values in this temporary copy. And after that, I reassign that temporary copy to the imputed trained DS variable. Here we can see the output. So over here we've got a couple zeros. They mustn't have had similar users or items. We've got my calculations and the original ones. So before I implemented my solution, we had a mean absolute error of 0.80, root mean square error of 1.02. And after my predictions, the mean absolute error is 0.74, which is similar to what they found in the original report, and root mean square error 0.95. Thank you for watching.